I am Lee Lowery with the Civil Engineering Department at Texas A&M University, and I will be presenting the statics review for the Fundamentals of Engineering exam to you today. The book that we sent to you for your use to study and review this exam, you probably have it in your possession. It's called the EIT Review Manual by Michael Lindeberg. We'll take some of the example problems out of this. It's a very complete book. I highly recommend you work all the problems in it that you have time to. But basically, the information that I present to you today will be geared towards the Fundamentals of Engineering Discipline-Specific Reference Handbook. This is the handbook that gives you all of the equations and information that they will allow you to take with you into the exam. We have talked to some of the people who actually made up this exam. One of them was Dan Turner. He presented information to you last time we sent a tape up. They guarantee us that if it's not in this book, it's not going to be on the exam. Now, of course, that does not mean that they will not find some challenging way to put together something that's in the book. But if you're wondering if you should study something rather complex, but you know you would need an equation to do that problem with, and you can't find that problem in this review manual, I'll put it here so you can see it a little better, then you can almost be assured that they will not ask you that question. You'll notice that one says review copy only, do not take to exam. They'll send you one for your use so that you can tinker with it and play with it and get acquainted with where the material is. But they won't let you take it into the exam. They'll give you a nice new shiny one when you get there. Now, the following sheets I'm going to show you, we have sent down to you. I believe there's about 50, 60 pages worth of material. This is the information that is in the book that we have to work with. There is a section called statics. It is only 2 pages long. There are many more problems that involve statics on the quiz than that, but this is the type of material we're going to cover. You'll notice I give you information on forces, resultant of forces, resolving forces from their components or taking components of the force, moments or couples, sets of forces or systems of forces. Once we get forces behind us, including forces and moments, we'll be doing centroids of various items. There's about another half a page of information or derivations or controlling equations for how to find centroids. Information on moments of inertia. You see some of this duplicated because when I blew it up it got a little larger. And moment of inertia transfer theorem. Again, part of your moment of inertia equation. They hint that they may indeed ask you information on how to find a radius of gyration used in column buckling work, how to find a product moment of inertia, back in some more traditional statics, friction. They got some things a little arcane, I would think, but if it's in this book, someone convinced these people that that was an important enough item to put in there, so we will cover it. Square thread screw jacks, brake band or belt friction, statically determinate trusses, plain trusses by method of joints and by method of sections, and then concurrent forces in 2 and 3 dimensions. Now, one of the interesting things you find in here that really seems to be left out is frames, and I believe the reason they left frames out of this information is because it is nothing but statics. They've already pretty well asked you to be able to put pieces of bars and stuff like that in equilibrium, And so I can pretty well assure you there's very likely to be a frame problem on there, so we'll cover frames also. We'll start from the beginning for anybody who's really forgotten all this stuff. If you already pretty well know this, you could, if you've got a tape on your own, you could advance it forward. First, let's take some forces, typical forces. The exam is going almost entirely now to metric units, so you'll probably see most of the problems in meters and newtons and that type of units. You should go ahead and get familiar with them. If you're unfamiliar with them, they're confusing for a while, but the more you work with them, they just become another way to buy some Rice Krispies by the newton instead of by the pound, so it probably won't matter much. There's two ways they would give you a force. Many times you will need to determine the component of these forces on a set of axes. They could give you the force and give you some angle, perhaps with respect to the vertical axis, perhaps with respect to the horizontal axis. You can draw a box around this force. The projection on the F-axis could be found by simply multiplying the original force, 260,000 pounds, and then you multiply that times the cosine of the included angle between the force and the axis that you have been asked to find that component. So since we've got 90 degrees in a right angle, we're talking about 72 degrees. Then 260 kips times the cosine of 72 degrees. I've got a friend of mine here with me running a calculator and the camera, so
80.3.
80.3. Now you should be able to also tell if it is reasonably accurate, because if this thing is about 260 inches long, then I would say indeed this side of this triangle is about 80 inches long. So 260 kips, about 80 kips is probably correct. To find the vertical component of the force, you'd multiply again the force you want the component of times the angle between the force and the axis upon which you want the projection, and that would be 260 kips multiplied times the cosine of 18 degrees for a total of
247.3.
247.3. Now, a lot of times the answers on your quiz will not be that close. They may just say 250 kips, but they are saying that give me the closest number. Is what they're looking for. You probably don't need 4 decimals of accuracy. Now, another way of asking you for components of forces would be when you know the slope of the force as opposed to the angle at which the force sits. Again, I draw a box around the force, and without getting any answers, without any help from a calculator, if this thing right here is 50, then I'd say that number there looks like about 30. So I ought to have some feel for what the number is. And if that's 50 and that's 30, this is maybe somewhere around 40. One nice thing about that is if you look on the quiz and the possible answers, A, B, C, D, E, one of them says the answer is 32, 47, 99, 106, and 10. Well, I don't have to do any work. I don't even need my calculator. And it's got to be that one there. But to get it accurately, you need to know the length of this hypotenuse for this short piece. You would take 5 squared plus 7 squared, the square of the two sides summed. Take the square root.
8.6.
Gives you 8.6. Give me a little more accuracy.
0.2.
Okay, so it was 8.6. 8.6 is how far it is along that hypotenuse. Now you could then find the cosine or the angle here by saying, give me the angle whose cosine is 5/8.6. But if you do that, when you find the cosine of this angle, it's just going to turn right around and be these two numbers. So you might as well just say how much this force points in the horizontal direction is 5/8.602 multiplied times the original 50 kip force. Therefore, the horizontal component is about 5/8 of the original force, and that comes out
29.06.
29.06 kilonewtons. Pretty close. Then the vertical component can be found by using the vertical side of this triangle. The vertical side of this triangle is 7, and that means the vertical projection of that force is 7/8.602 multiplied times the original magnitude of the force. 7/8.602 kilonewtons times 50 kilonewtons is
40.69.
Yeah, that's guessing much more accurate than you have any hope of getting. 40.69 kilonewtons. So that's just luck those came out that close. Now, sometimes you will be given a pair of forces, and you will resolve them into one single force. We would do the same thing. We would get the horizontal projection of the 7.5 kip force. We would then find the horizontal projection of the 11.5 kip force. We would add them together for the single force that would act in the horizontal direction and be able to replace these two. Alright, now then, we're going to take the horizontal component of the F1 force. We'll multiply 7.5 kips times the cosine of 45 degrees, and this projection on this axis then would be 5.30 kips. We'll take the horizontal projection of the 11.5 kip force, and we get 11.5 times the cosine of 30. That gives us 9.96 kips. We add both of them together, and it comes out a total of 9.96 plus 5.30, 15.26 kips. Then we do the same thing for the vertical components. Draw a box and get the vertical component. We draw a box, we get the vertical component. They look about the same, really. That's assuming they were drawn to scale. If you multiply 7.5 times the cosine of 45 degrees, you get 5.30. If you multiply 11.5 times the cosine of 60 degrees, this being 30 degrees here, then you get 5.75 kips. So 5.30 kips pointing down, 5.75 kips acting, up, 5.75 kips acting down, gives you a total down, the difference of the two, 0.45. And there is some force that I could draw which would personally have this much horizontal component, 15.26, and this much vertical component, 0.45. I could easily get that by just drawing that same little box around this unknown force. That force is probably given the name something like R. You could find R by squaring the two sides. 15.26 squared plus 0.45 squared. Take a square root of the sum. The magnitude of this force would be 15.27 kips. Now you can also find the angle at which this force sits. This is the resultant of the original two forces we had. We had a 7.5 kip force and an 11.5 kip force. You could replace those with their resultant, 15.27 kips in magnitude. The resultant force has to push down and to the right because the components of the original two forces summed down and to the right. You can find this angle right here, theta, by using the tangent of that angle is opposite divided by adjacent. So the tangent of theta would be opposite 0.45 divided by 15.26, and if you hit arctan on your calculator, you find that angle to be 1.69 degrees. So that's how you would take a force and resolve it in a pair of forces or many forces and resolve them into a single resulting force. Here would be a third example. It's on page 11. In this case, we have a 140 Newton force at 45 degrees, a 75 Newton force at 30 degrees, a 130 Newton force at 15 degrees. We would do the same thing as before. We'd box in each of these forces in order to see what their components look like, about how big their components project on each of the axes. To find this horizontal force, you would multiply the force times the cosine of 15 degrees. To find its vertical, you'd multiply 130 newtons times the cosine of 75 degrees, the complement of this 90-degree angle. Then you would have the 75 Newton force times cosine 30 and cosine 60. Then you'd have the 140 Newton force times cosine of 45 and cosine of 45. And I don't care if we work out those numbers as long as you know what we're doing here. You'll then be able to add this particular horizontal force, subtract this horizontal component, subtract this horizontal component, and the resulting sum of those three numbers would be the total horizontal projection of one single resultant for these three forces. Then you do the same thing for the vertical components. You multiply F3 times the cosine of 45 degrees. You'd multiply F2, 75 Newton force, times the cosine of 60 degrees, this one being 30. And you'd multiply this 130 Newton force times the cosine of 85. That would give you vertical components. So anytime you want the component of any force on any axis, all you do is you multiply the magnitude of that force times the cosine of the included angle. Anytime you want the components of a force that is given in terms of slope, instead of in terms of angle of degrees, for example, you might have a force that is 200 newtons. Say this is a 5, this is an 11. In other words, the slope of that angle is rise of 5 and run is 11. Then I would take 5 squared plus 11 squared. Take a square root to find out how long this piece right here is.
12.08.
12.08. And I can tell you now that the horizontal component of this 200 Newton force is the original force, 200 newtons, multiplied times, to get the horizontal component, I take the horizontal side of the angle, that's 11, divided by the whole, the hypotenuse, the 12.08, and that gives me the horizontal component equal to
182.1.
182 newtons, which looks about right. If that one looks 200 long, that looks about 182. By the same token, this number should be 200 multiplied times 5 over 12.08. 12.08. Because 5 is the vertical side of the triangle, and you're looking for the vertical side of the components, which is equal to
82.8.
82.8. All right, a typical problem on the exam this one came out of the review manual. It's on section 1010 in your manual that we sent you. Would be 3 forces given the angles at which those forces sit. And your choice is which one of these is the appropriate resultant of this set of forces acting on this steel hook. To get that, you'd multiply 1,000 times the cosine of 30. From that, you would subtract, because it's going to the left, 750 times the cosine of 15. From that, you would subtract 1,500 times the cosine of 20, and you'd sum all those 3 horizontal components, and that would give you the horizontal component of the answer. To get the vertical component, you'd multiply 1,000 times the cosine of 60 degrees. You can use the sine of 30 if you want. That's obviously the same thing. If you're a little rusty on this, I would just always take the force and multiply it times the cosine of the included angle. That way you'll never have to try to remember if you're supposed to use sine or cosine. So that's 1,000 times the cosine of 60 degrees. I would call that a plus number because the force is pushing up. From that, I would subtract 750 times the cosine of 75 degrees. 7 of 80, 90, that's right. To that, and I would call that a minus because this component, or this force, is pointing down, and he's pointing to the left. This guy's pointing up and to the right. This guy's pointing up and to the left. So then the last number is a 1,500 Newton force multiplied times the cosine of 70 degrees. Got the sum of those yet?
Yes, sir.
What does that come out?
Minus 1,268.
Alright, add those up, 1,268 newtons, and the plus minus plus 819 newtons, and therefore we should be able to find the one force that would resolve all these forces into a single force, and that number would be 819 squared plus minus 1268. That's not going to matter because it's going to square. Take a square root and you get
1509.
and therefore there's your answer. So about 2 minutes after you start, you got an answer, and that's usually what they're looking for, about 2 minutes per problem. All right, another typical example is trying to find forces that would keep something in equilibrium. In this case, I have a cable tied at points A and B to support a mass, and we could say that mass is equal to 10 kilograms. And then I could ask you how much force is necessary to keep these forces in equilibrium, to keep the mass supported. To do that, you need a free body of the connection point. So we would show the connection C. If you're asked what the forces are, you need to be careful. A lot of times they'll give you this in terms of kilograms instead of in terms of a force. And one of the answers probably will be without the 9.86 attached to this number to change this mass into a force. So I'll show a force down 10 kilograms multiplied times 9.81 meters per second per second. If you've forgotten why that is, it's almost impossible to forget F equals ma. Force equals mass times acceleration. If force equals mass times acceleration, then here's your force over here. It will be something like newtons. The mass will be kilograms, and you can tell you got a problem there because mass isn't going to equal to a force. And what do you have to multiply it to make it a force? You multiply it times g, and that's 9.81 meters per second per second. And a kilogram meter per second squared is the same thing. They gave that assemblage of units the name newtons, and so that's why we got to multiply times 9.81 to turn it into a force. Now, on this side, we have a force. It's absolutely critical that when you cut this wire and show a free body down here, you do two things. Number one, you must give this arrowhead a name. A good name for that one might be FCB. It's an acceptable name since it's cut through CB. And you'll notice that I gave the arrowhead a direction. It's probably pretty obvious that the force is a pulling force, a tensile force, since it's a cable and since the weight is pulling down on the cable. But a lot of times in the structures you'll be asked to solve, you don't know the direction of this arrowhead. Many people say, well, since I don't know what the arrowhead's direction is, I'm just not going to put it on for now. I'll put it on later on when I find out. You can't find out. It's absolutely impossible. The only thing you can do is to guess it goes some way. And when you solve for the answer, if the answer comes out with a minus sign in front of it, that means you guessed that arrowhead on the wrong end. But without putting it on there first, you cannot solve for which way this arrowhead pulls or pushes. Alright, so we have 30 degrees in here. We have a second force that's been cut. I'm going to put an arrowhead on it. That's a guess. It's a pretty good guess. It's probably even correct, but it is nothing but a guess for right now. And that would be the force in member AC. It sits at an angle of 45 degrees and 45 degrees, and of course this one in here then is 60 degrees. Now, in order for this thing to remain stationary, you have a pair of equations that tell you that the sum of the forces in the horizontal direction must be 0, otherwise the thing will accelerate to the left and right. We can find out what the sum of everybody pushing in the right and left direction, just like we did a minute ago, by finding the components of these forces. First, we take a look at this force. This force has no horizontal component. Therefore, we don't enter him into this equation.